So let's have a look at this next bunch of examples. Again, if you haven't done so already, pause the video, go ahead and work on these examples. If there's any that you struggle with, then quickly navigate to that portion of the video and you can see how I work through it. So let's look at the first one. The integral from 1 to e of ln of x over x dx. Any knee-jerk reaction at this point? Just what do you think we should do? So since we see that the logarithm on top has its derivative, which is 1 over x, in the integrand as well, we should maybe substitute for the ln of x. So that's what we're going to do. We're going to take our integral from 1 to e ln of x over x dx. We're going to make this substitution. U equals ln of x, du equals 1 over x dx. It's a definite integral, so we can also replace our limits of integration as well. So what are our limits? They were e and 1 in the new variable. The upper limit becomes ln of e, which is 1, and the lower limit becomes ln of 1, which is 0. So there's our substitution. And so this becomes the integral from the new lower limit to the new upper limit. And the logarithm gets replaced with u, and the 1 over x dx gets replaced with du. So this becomes a u du, which I can anti-differentiate as 1/2 u squared from 0 to 1. And so our result is 1/2. How about the next example? The integral of cos squared of 5x. And this is one that we see quite frequently, and it should automatically come, or fairly quickly it should come to you, that perhaps use a trig identity. And what's the trig identity? It's the one that we can use to drop a power off of the cosine function. So cos squared is 1/2 plus 1/2 cos 2 theta. This allows us to drop the power on the cosine function from 2 to 1, and then we can anti-differentiate the cosine of 2 theta. So that's what we're going to do. We're going to use this identity here. We weren't dealing with theta. Our argument is 5x. So we'll just see how that works out. Cos squared of 5x dx. Rewriting that expression, that's 1/2 plus 1/2 cos of double the angle. So the original, or double the argument. The original argument is 5x, then doubled argument is then 10x dx. Now we can anti-differentiate. That's 1/2 x plus 1/20th sine of 10x plus c. And so there is our result. How about this next example? The indefinite integral of x cubed ln of x dx. What should we do there? So we've got a product of these two functions in the integrand, the x cubed and the ln of x. This might be a point to think about by parts, because maybe I could imagine pushing the derivative off of one onto the other. That's sort of what the by parts method is doing. What one should I take for u, and what should I take for v? So by parts, u is equal, dv is equal to, what should we do? If I took u to be part of that integrand that I can differentiate, and dv to be the part that I can integrate, then it seems that the logarithm, that's easy to differentiate. When I differentiate it, it becomes a 1 over x. And that's nice because the logarithm goes away, and now I've got left with the power of x on the bottom. And this x cubed, I can integrate it. That would give me an x to the 4th. So it seems that maybe at this stage, this would be a good option. So let's carry through the details of that then and see what happens. So we're going to take u to be ln of x, dv to be x cubed dx. When I take the derivative, I get du is 1 over x dx, and v is equal to 1/4 x to the 4th. Now we know we'll be successful in applying by parts if we can find the antiderivative of the product of these two things, the v du. And the product of those two things is just going to be a quarter x cubed. And I know how to find the antiderivative of x cubed, so at this point we know that we're going to be successful in applying by parts. Now we just have to go through the details. So this is a quarter x to the fourth ln of x minus the integral of the product of these two. So integral of 1 over x times 1 quarter x to the fourth, so that's 1 quarter x cubed dx. So that's 1 quarter x to the fourth ln of x minus 1/16 x to the fourth plus c. And we're done. Okay, so oftentimes you're trying to figure out what to do. Maybe you try to do by parts, find the dv or du, find the v, and just take a quick look. Is the product of v du something that you can anti-differentiate? If it is, then proceed with by parts. If it's not, think about if it's something you could actually do with a little bit more work, or whether you should go back and rethink taking by parts in the way you've done it, and maybe try substitution or some other method. So it's a lot of trying something, seeing what happens, trying something else, seeing what happens, and relying heavily on the fact that you know a lot of the basic antiderivatives given in the table at the beginning of these notes. Let's look at the next one, part D. What's the question? X secant x squared tan x squared. So the antiderivative of x secant x squared tan x squared dx. So first thoughts, what should we do? Well, when we look at this, we see there is part of the integrand whose derivative is also in it. If I look at the x squared, its derivative is x. So that's a good place to start. Start with a substitution. Get rid of some part of the integrand to focus your attention on the other parts. So this is sort of like realizing what the inside function is so that you can focus on trying to find the antiderivative of the outside function, imagining that this was coming from the derivative of a composition using a chain rule. So what's u? U is x squared. Du is equal to 2x dx. So that x dx can be replaced with 1/2 du. And then the secant and tangent survive. They're just secant u and tan u. And what function has a derivative of secant u tan u? That would just be secant u plus c. And so that's now back in terms of our original variable x. We get that the result is 1/2 secant of x squared. So let's look at the last example now. It's the integral of 3x plus 1 x times x plus 1 dx. Now for this one, it's a rational function, so this means that we should probably look at using partial fractions. Maybe we shouldn't jump too quickly to using partial fractions, because at this stage we probably should just look, is the derivative of the bottom the thing on the top? If it is, then a substitution would work. If the derivative of the thing on the bottom is not the thing on the top, then partial fractions is probably the way to go here. And I look at the bottom, and it's an x squared plus x. The derivative would be a 2x plus 1. That's not what's up top. So perhaps we should use partial fractions here. So to use partial fractions, what we have to do is just rewrite the integrand in this way. Something over x plus something over x plus 1. Now, I can fill in arbitrary constants a and b above those and then do the normal process of partial fraction decomposition, try to figure out what that a and b have to be using a bit of algebra. Or I could just maybe do it by inspection. I see that 1 sitting up there. The only way that 1's going to come up is it's going to be the product of what's sitting above the x with that 1 in the denominator of the second term. So I know immediately that there has to be a 1 there. And if that's a 1, then when I collect these things over a common denominator, multiply x plus 1 to 1, so that becomes an x plus 1, plus whatever's over here times x has to be 3x, so I know that has to be a 2. So there's the decomposition. And therefore, the antiderivative is ln of absolute value x plus 2 times ln of absolute value of x plus 1 plus our arbitrary constant of integration. And so there's our result. Maybe just for fun, we'll try an alternate method for this. Let's just put it down in a different color. Generally speaking, for all of these antiderivatives, there's more than one way to go about doing it. Let's see if we can find an alternate method here. So I'm going to go 3x plus 1 over x squared plus x dx. So there's our integrand. Now, I noticed that if this was a 2x rather than a 3x on top, if it was a 2x, that would be a direct substitution because the derivative of the bottom would be the thing on top. But it's not a 2x, it's a 3x. However, I could write it as a 2x plus 1 in this way. Now it's 2x plus 1, but there's also this plus x because the real numerator had a 3x there. Okay, have I made any progress? Well, now I can split the integral up into two integrals, an x over x squared plus x dx. Plus the integral of 2x plus 1 over x squared plus x dx. Now the nice thing about this is that second integral we can do directly with the substitution. The first one, there's this common factor of an x that can cancel. So this becomes a 1 over x plus 1 dx. And this other one, we're going to get by just doing a direct substitution. The antiderivative of this becomes ln of x plus 1. What's the antiderivative of this? Well, the denominator's derivative is exactly the numerator. We could substitute u equals the denominator, see that the derivative is the numerator, and if you do that, you'll get an integral of 1 over u du. You anti-differentiate, put things back in terms of x, and that's your result there, plus c. Now, is this the same thing that we had before? If I look back at my answer previously, well, it doesn't look the same, but it is. How do we know it is? Well, I can write this logarithm as the logarithm of x times x plus 1. The logarithm of a product is the sum of the logs. So that's ln of x plus ln of x plus 1. Now I've got two of these ln of x plus 1s. Plus an ln of x plus c. And that's our answer that we had written above. So again, an alternate way to look at it, and we end up with the same result.